Hello viewers, today we are starting with a new series on reactive methylene compounds. Let us ask ourselves a few questions in order to familiarize ourselves with few basic concepts of this topic. What do we mean by a reactive methylene compound? What is a reactive methylene group? Why are compounds containing reactive methylene group so reactive in nature? First, let us see what is a methylene group. When we remove a hydrogen from methane, we get a methyl group. And when we remove two hydrogens, we get a methylene group. This methylene group is not acidic in nature, since the hydrogen here is attached to an sp3 hybridized carbon, and there is very little difference in electronegativity of carbon and hydrogen. On the other hand, when a methylene group is located between two electron withdrawing groups, this group becomes reactive in nature and we call it as active methylene group. The class of compounds containing a methylene group directly attached to two electron withdrawing groups are called active methylene compounds. So let us look into what is the general structure of an active methylene compound. As you can see on your screens, a CH2 group is attached to two groups which are E1 and E2. These E1 and E2 are electron withdrawing groups. That is, when they are attached to the methylene group, they will pull the electrons towards themselves. I have depicted this in another manner, in which you can see a methylene group sandwiched between two electron withdrawing groups, in which the L1 electron withdrawing group is an ester group. And this other electron withdrawing group, which is Z, may be a acetyl group, it may be a nitro group, or it may be a cyano group. Now let us look into some examples which are containing methylene group. On your screens, you can see the structure of ethyl acetoacetate, which is also known as ethyl 3-oxobutanoate. Why is this known as 3-oxobutanoate? Because the longest carbon chain here has 4 carbons in it, which is derived from an acid, that is 1, 2, 3 and 4. And at the third carbon, we have a ketonic group. So this compound is known as ethyl 3-oxobutanoate. In this CH2 is a reactive methylene group because it is sandwiched between one ester group, which is an electron withdrawing group, and the second electron withdrawing group here is the aceto group. The next example is that of Melonic Ester. In Melonic Ester, the methylene group is sandwiched between two ester groups. And Melonic Ester is an ester of melonic acid, and melonic acid and ethanol. And we know melonic acid is a dibasic acid, or it's a dicarboxylic acid, which is CH2, COOH, and again we have a COOH. In this case, this methylene group is sandwiched between two ester groups. One ester group is this, and this is the second ester group. So this group, methylene group, is again a active methylene group. The next compound that I've shown on your screens is that of a cyanoester. And what you can see in this case is, that is, we have ethyl cyanoacetate. And in this case, again, the two electron withdrawing groups are COOET, ethyl group, that is ethyl group, and this is what? This is again an ester, and here we have a cyano group. And both these groups, the ester and the cyano, which are the electron withdrawing groups, are sandwiching a methylene group, which is again a reactive methylene group. And this compound is another example of compound having a reactive methylene group, and we call it as compound having again a reactive methylene group. So what are the examples of electron withdrawing groups? As we've seen, a acetyl group, an ester group, a cyano group, and a nitro group are electron withdrawing groups. And when these groups sandwich a methylene group, that methylene group becomes reactive in nature, and such compounds are known as reactive methylene compounds. Now the question is, why is this methylene group, which is sandwiched between two electron withdrawing groups, so reactive? It is because the hydrogen of active methylene group is acidic in nature, and this is responsible for unusual reactivity of methylene group, or in other words, the compounds which are containing this reactive methylene group are reactive and are important synthons. That, as you will see in the following lectures, we will be preparing a variety of compounds from ethyl acetoacetate, which we shall be discussing in great details. But before we start with the discussion on the acidity of hydrogens of a methylene group, let us understand as to what makes this hydrogen so acidic, whereas hydrogens of methane are not. As I've already said, that hydrogens in methane are attached to a carbon which is sp3 hybridized. And we know that an sp3 hybridized carbon is not very electronegative. Second, there is very little difference in electronegativities of carbon and hydrogen. Or we can say that carbon and hydrogens have similar electronegativities, which means that the bonding pair of electrons are equally shared between carbon and hydrogen. Or we can say electron binding these two atoms are equally shared. Therefore, between these two atoms, therefore this bond is strong and it is difficult to break it. Right? So because of this bond being strong, this hydrogen is not acidic in nature because it cannot go off as H+, that is, it cannot dissociate as H+. And pKa value of ethane is equal to 50, which indicates that this ethane is not acidic in nature. On the other hand, if hydrogen is bonded to an sp3 hybridized carbon that is adjacent to an electron withdrawing group, then that hydrogen is acidic in nature, or it is more acidic than hydrogens which are bonded to other sp3 hybridized carbons. Please remember, the carbon which is next to the functional group, that is, which is next to the electron withdrawing group, is alpha carbon, and the hydrogens attached to this alpha carbons are known as alpha hydrogens. Here I have on your screens, you can see three examples. First is an example of Ethane Nitrile, and what we find that this hydrogen in Ethane Nitrile is acidic in nature, which is indicated by a yellow color, and it is shown by a separate bond here. I wanted to distinguish between these two types of hydrogens, that this methyl group has 3 hydrogens, and this hydrogen we are showing is acidic in nature. And if we talk of an ester, which is ethyl acetate here, again the hydrogen which is attached to alpha carbon is acidic in nature. If you look into nitro ethane, then what we find that this carbon is the alpha carbon and this carbon is the beta carbon, that is the carbon which is directly attached to nitro group is the alpha carbon and the next carbon is the beta carbon. The hydrogen which is attached to alpha carbon and is indicated by yellow is acidic in nature, whereas the hydrogen which is attached to the methyl group of nitroethane is not acidic in nature because it is away, that carbon is further away from the nitro group, and we know that the minus I effect or plus I effect, that is the inductive effect, decreases as we go away from the electron withdrawing or an electron donating group. So now we know that a compound that contains a relatively acidic hydrogen bonded to a sp3 hybridized carbon is called a carbon acid. Why is it called a carbon acid? Because the hydrogen which is bonded to the alpha carbon can dissociate and can be given off as proton. So we call it as carbon acid. Now I would like to discuss with you the acidity of a compound which is having a carbonyl group in it, that is that of an aldehyde or a ketone with alkane, and here we've taken examples of ethane for alkane. So what, as you can see on your screens, the pKa values of aldehyde and a ketone are between 60 to 20, whereas a pKa value of ethane is 50, which clearly indicates, the higher pKa value of ethane clearly indicates that the hydrogen of ethane is not acidic in nature. Whereas the alpha hydrogen of an aldehyde or a ketone is acidic in nature because this hydrogen is attached to a carbon which is next to an electron withdrawing group. In case of an aldehyde, the electron withdrawing group is CHO, whereas in case of a ketone, the electron withdrawing group is COR. So let us ask ourselves a question here. Why is a hydrogen bonded to an sp3 hybridized carbon that is adjacent to a carbonyl carbon so much more acidic than hydrogen which is bonded to other sp3 hybridized carbons? A carbon bonded to an alpha carbon is more acidic than hydrogen bonded to other sp3 hybridized carbons because the base formed when the proton is removed from an alpha carbon is relatively stable, and we know if the base is stable, the conjugate acid will be acidic in nature. So why is the base formed by removing a proton from an alpha carbon more stable than bases formed by removing a proton from other sp3 hybridized carbons? The reason is, when a proton is removed from ethane, the electrons left behind reside solely on sp3 hybridized carbon atom. And we know that sp3 hybridized carbon atom is not electronegative in nature. So what will happen? The carbanion formed is not very stable, because here the electrons are localized over carbon, which is not electronegative. So it will not be able to adjust that excess negative charge. So it is not formed, and if it is formed, it is not stable. Hence, the alkane or ethane is not acidic in nature. As you can see on your screens, the carbanion formed from ethane is not stable, because here the electrons are localized on sp3 hybridized carbon, and its pKa value, as we've already discussed, of this acid is very high, that is, it is 50, and hence it is not acidic in nature. In contrast, when a proton is removed from an alpha carbon, which is adjacent to a carbonyl carbon, two factors combine to increase the stability of the base that is formed. First, the electrons left behind when proton is removed from an alpha carbon are delocalized. And the delocalization of electrons increases the stability of the anion. And most importantly, the electrons are delocalized onto an oxygen atom. An atom which is more electronegative than carbon can accommodate the electrons more efficiently. As you can see on your screens, I have shown that when an alpha hydrogen dissociates and this bond dissociates, and this alpha hydrogen is given off as proton, we get a carbanion. And in this carbanion, since there is conjugation between this non-bonding pair of electrons and the pi bond of the carbonyl group, resonance can take place. And as a result of resonance, this negative charge is now delocalized over carbon and oxygen. Reason being that oxygen, being more electronegative in the carbonyl group, will pull the electrons towards itself, as a result of which the carbon will have a positive charge. Now these electrons will make a double bond between these two carbons. So as you can see in the next structure, these electrons are on oxygen, and we know that electrons are able to accommodate these electrons better. Therefore, molecules having alpha hydrogen or a group, methylene group, which is attached to an electron withdrawing group, are more acidic than alkanes. Let us discuss another example where an alpha carbon is between two carbonyl groups. So what will happen to the acidity of hydrogens of this methylene group, which is sandwiched between two electron withdrawing groups? We find that if the alpha carbon is between two carbonyl groups, the acidity of the alpha hydrogens will be even greater. For example, the pKa value for dissociation of a proton from an alpha carbon of 2,4-pentane dione is 8.9. That is, it is even more acidic than a compound from an ordinary aldehyde or a ketone. So what we find in 2,4-pentadione, the methylene group is sandwiched between two acetyl groups. Therefore, the pKa is 8.9. This 2,4-pentane dione is also known as acetyl acetone. Why is it known as acetyl acetone? Because one of the hydrogens is replaced by an acetyl group. So if we are now comparing the acidity of acetyl acetone and acetone, acetyl acetone will be more acidic, that is the hydrogens of alpha carbon that will be more acidic, that is they will be able to dissociate faster because that group is sandwiched between two electron withdrawing groups. And I want you to again have a look at the slide. That is, this is known as beta ketone. Why is it known as a beta diketone? Because when we start numbering from here, so we get this ketonic group is at the beta carbon. So we call it as beta diketone. Now let us go on to why is the acidity of alpha hydrogens which are bonded to two electron withdrawing groups increase, or why is it more? So what we find that when the carbon ion which is formed as a result of dissociation or removal of proton from this methylene group, which is sandwiched between two electron withdrawing groups, is more stable. That is, here the negative charge can now be delocalized onto either of the two oxygens of the acetyl groups. As you can see on your screens, that is, this is the reactive methylene group because it is sandwiched between two electron withdrawing groups, and a hydrogen has been removed from here as a proton, and we get a carbon ion. Now the carbon ion which is formed, you can see we made two resonating structures for this, and in these two resonating structures what we find that oxygen that negative charge can be delocalized over these two oxygens. In this structure we have a double bond between CH2 and C here, and the negative charge is on oxygen here. Whereas in the next structure, the second structure, the lower structure, again the negative charge is on oxygen and the double bond is between C and CH. So if you just try to visualize the resonance hybrid for this structure, so what you will find that we will have a negative charge on both the oxygens, and a partial double bond will be stretched between oxygen, carbon, CH again, and carbon and an oxygen. That means the negative charge is delocalized. That means this carbon ion is highly stable, and therefore the hydrogens which are attached to the methylene group in this case are acidic in nature. Now let us go on and discuss the acidity of the methylene group of ethyl acetoacetate. And we shall be discussing this ethyl acetoacetate in great details, taking it as an example of a reactive methylene compound. So here also what we find that the alpha hydrogen atom here, or the methylene group, is sandwiched between two electron withdrawing groups. And these two electron withdrawing groups one is an ester group and the other one is an acetyl group. So that means that these two electron withdrawing groups will pull the electrons towards itself, that is because of the minus I effect. So when they pull the electrons towards themselves because of the minus I effect, the bond between carbon and hydrogen will become weak. As a result of which this hydrogen, the bond will dissociate, and hydrogen, the bond will break, and the hydrogen will be eliminated as proton. So we say the two hydrogen atoms bonded to methylene group become acidic and reactive due to two electron withdrawing functional groups, as we've already illustrated that one of the group is the acetyl group and the other one is the ester group. So as I've said that the CH bond will be weak, H will be given off as H plus, and what the carbon ion which will be formed will be highly stable, and therefore we say the hydrogens of this methylene group are acidic in nature. So that means if a methylene group is sandwiched between two electron withdrawing groups, which may be, both the groups may be acetyl groups, as in case of a ketone that we studied, that is pentane 2,4-dione, or if we take a case of ethyl acetoacetate, where the two electron withdrawing groups are the ester group and the acetyl group. So as a result of these, this H plus becomes, the bond between this carbon and hydrogen becomes weak, and this H is given off as H plus, and we get a carbanion, as you can see on your screens, which is stable. Here again I have illustrated the same thing which I have explained, that these two groups exert a minus I effect, due to which this carbon becomes electron deficient. It will pull the electrons towards itself, and the bond between carbon and hydrogen will become weak, and this hydrogen is given off as proton, resulting in the formation of stable carbanion. And the resonating structures which we get of this carbanion, as you can see on your screen, are again highly stable, because the negative charge on this carbon, that is the carbon of the methylene group, can be delocalized over oxygen of the acetyl group and over oxygen of the ester group. So here it is delocalized over oxygen of the acetyl group, and in this case it is delocalized, the negative charge is delocalized over oxygen of the ester group. Why is this happening? Because there is conjugation here, and we know that resonance takes place when the double bond or a negative charge are in conjugation. And as you can see, now this structure, resonance hybrid, is highly stable, as I had explained in case of the anion of pentane 2,4-dione. That is, the negative charge is delocalized over two oxygens and carbons, and here we have a partial double bond. So we say that the negative charge is delocalized, and since the negative charge is delocalized, this is a highly stable anion. So in this lecture, I have discussed with you the acidity of hydrogens, and we've concluded, or we can make a conclusion here, that a hydrogen which is attached to an sp3 hybridized carbon, say in example of ethane, that hydrogen is not acidic in nature, because there is no or very little difference in electronegativities of carbon and hydrogen. And once if we remove the proton from there, the negative charge will be on sp3 hybridized carbon, and that carbon is not able to adjust that negative charge. Whereas if this methylene group, so now we can conclude that the hydrogen which is attached to an sp3 hybridized carbon, as in case of ethane, is not acidic in nature, because the carbanion formed will not be stable, since the negative charge is localized over sp3 hybridized carbon. Whereas if a methylene group is sandwiched between two electron withdrawing groups, then the carbanion formed is stable, because the negative charge is delocalized over the whole of carb anion. That is, if we are taking an example of ethyl acetoacetate, the negative charge is delocalized over two oxygens and the methylene carbon. We shall be using this concept further in my next lecture, when we shall discuss tautomerism, and with that we shall also be discussing tautomerism and ethyl acetoacetate, because tautomerism has been studied in great details with ethyl acetoacetate, and that means we should give a second glance and concentrate more on tautomerism of ethyl acetoacetate. Thank you.